Thank you. So thank you all for being here. It's great to see a full auditorium. So what I'm going to talk about today is I'm going to kind of give a tour of what we know about the universe, where we are in the universe, how we study these things. So I'll start with saying a little bit about cosmology and about sort of my career and how science can take you places in the world. So, okay, so what is cosmology? It's really the big questions, okay? The questions like, what is the nature of the universe? What are its components? Where did it all come from? How did it begin? And how will it end? And these are the kinds of questions that we can use data, observations, experiments to learn about in the modern world. In order to get to the point where you do academic research in cosmology, you have to go through a number of steps. So for me, I started out in Long Beach, California, in the US. And from there, I went to Caltech for my undergraduate degree in physics, got a PhD in astrophysics at Princeton, and then I went to Cambridge University for my first postdoctoral research fellowship. So a postdoctoral research fellowship is where you sort of begin your career as an independent researcher. And then I went to Melbourne, and that's where I've been for the last few years. And in the next stage, I'm going to head back to the States and start a professorship at North Carolina State University. So this is a very international field, and scientific research in academia really takes you all around the world. So this is just a map of some of the places I've been for physics. So these are some conferences, collaboration visits, places where I did some research project, some teaching, all of that stuff. And this is all work travel, so universities send you all over the world to do science if you're a researcher. So that's one of the perks of a job like this. So anyway, I'm going to begin the tour. Okay, we are here. This is a photo I really appreciate. This is from the Apollo 17 mission from 1972. This is sometimes called the blue marble picture. This is one of the first images taken by a human of the entire world all at once. During that era of exploring the moon, people were first able to kind of look back and see the entire planet unified all at once and sort of hanging in space as this, beautiful, delicate thing. Okay, so we live on the Earth, and back in the day, the idea was that the Earth was the center of the universe, and the moon and the planets and the sun and the stars all orbited around the Earth. That was replaced by a model where the sun is the center of the universe, and the Earth is just one of many planets orbiting around the sun. And when this was discovered, this started what's known as the Copernican revolution. So this is the recognition that we are not the center of the universe. We're just some part of the universe that's not the most important thing. And that led to what we call in cosmology the Copernican principle, which is that we do not occupy a special place in the universe. And that's something that's really important for understanding not just sort of where we are in the cosmos, but understanding how we can study the cosmos. Because if our little part of the universe is not unique and special, that means that we can study things nearby and learn about the cosmos as a whole and really try and understand that. So the Copernican principle is sometimes also called the cosmological principle, and it seems to hold true when we look at the universe on the very largest scales. The place we are is not a particularly special place. But we live in a solar system where we orbit the sun. We also live in a galaxy. This is an image of the Milky Way stretched across the sky. That's looking into the center of the galaxy. We're fortunate here in the southern hemisphere that we can do that. In the north, you can't see the center of the galaxy. So if we were able to sort of stand back and go above the galaxy, it would look something like this. This is just an artist's impression, where the galaxy has this kind of central bulge with a lot of stars and gas and dust, and then there are these spiral arms coming out, and the spiral arms make this kind of thin disk of a galaxy, and we're kind of out here, sort of near the edge. Now our galaxy has something like several hundred billion stars in it, and it's not unique. There are many other galaxies in the universe. And these were first sort of seen in the 1700s, where astronomers first started to calculate the little blurry things in the sky, or started to observe them and catalog them. And everywhere we look in the universe, we see other galaxies with their own sets of millions or billions of stars. This is a famous picture from the Hubble Space Telescope, where they took the Hubble Space Telescope and they just stared at a blank, uninteresting part of the sky for something like 10 days, just to see what was there, just to see what they might pick up. And what they saw was over 3,000 galaxies in this picture. So in this is a small piece of the whole picture. But in this, you can see this thing here is a star, and that up there is a star, and pretty much everything else is a galaxy. So another collection of millions or billions of stars. So that's a galaxy, this one, that one. All of the little colored specks there are individual galaxies far in the distant universe. And we've seen this kind of everywhere we've looked. There was another project like this. This is the Hubble Ultra Deep Field. So this was a few years later with a better camera. And the Hubble Space Telescope looked at a different part of the sky and again saw thousands and thousands of galaxies. There was something like 10,000 in this picture. Here's a star. There's one up here, I think. You can usually tell the stars in these pictures because they have little diffraction spikes on them. That's from how light is scattering around in the telescope. Anyway, just in case you see pictures like this and you want to know which ones are galaxies. So we see galaxies like this everywhere, and if we look even deeper, we see even more. So the Hubble Space Telescope then went and looked at that same field again and filled in even more galaxies in this picture. So the universe is really just teeming with galaxies, and we can chart out where they are. We can look in a few individual spots and see lots of them, but we can also make maps of the distribution of galaxies throughout the universe. So the Sloan Digital Sky Survey was one attempt to map out large parts of the cosmos. And the way that they did this survey was they kind of looked at the sky in stripes. So they'd sort of scan across one stripe of the sky and catalog all of the galaxies they could see along that stripe. And it would kind of make this sort of fan out from the Earth. And then they'd take another stripe and they'd do another one. So this little video is a zoom out from the Earth based on a reconstruction of that data. So in this video, all of the galaxies that you see are actual galaxies that have been charted and mapped from the Sloan Digital Sky Survey. So you can see us, we're sort of zooming out in the universe, and you can start to see that map. Here in the center, this part has more galaxies because that's one of the stripes that they went along. So we're coming out through one of those sort of slices of the universe. But one of the things you can see as we zoom out is that the galaxies aren't just uniformly distributed across the sky. They're kind of clumpy. So there's sort of a clump over here and one over here. And they end up making this kind of web-like structure. We call that the cosmic web. And it consists of sort of clusters of galaxies, big voids, filaments that stretch across millions of light years. And so we'll see that more when this video starts to rotate. You can see that in each of these slices of the universe, you can kind of see that web-like structure of how galaxies are laid out in space. And we can do simulations of how galaxies are laid out in space and see that cosmic web in even more detail. So this is a simulation where you can see that this would be sort of a cluster of galaxies there, and then a filament and a big cosmic void. And kind of everywhere we look, we see that similar pattern. And it seems that just kind of continues, that our little part of the cosmic web is not a special part of the cosmic web. It sort of carries on in a similar fashion as you go farther and farther away. Now in this survey, they didn't just look at the galaxies, they also looked at something called a quasar. So as you zoom out even more, these little blue dots represent quasars. Now quasars are extremely bright sources of light and that come from supermassive black holes. So you might have a picture in your mind of a black hole like this, so a black hole being something that sort of sucks stuff in. Black holes in some sense are defined by the idea that light cannot escape them. So anything that falls into a black hole can't come out again, and that includes light that goes in. So you'd think that they'd be dark or invisible. But it turns out that because other stuff can fall into a black hole, you get these sort of whirlpools around black holes, and those can light up extremely brightly. So this is another sort of drawing of a black hole in astronomy. And what you have is you have a black hole in the center there, and then there's all this material that's sort of funneling in. And as it's coming in, the gravity is really strong, and it pulls the matter in, and it swirls around really, really quickly, and it sort of collides and heats up and ends up glowing in high energy radiation, so like X-rays and gamma rays. And sometimes you get a situation where you have strong magnetic fields, and those magnetic fields can twist up and create jets that go out from the disk. And so those jets can also be extremely bright depending on which direction they're sort of facing. And those jets can be extremely powerful as well. Because the black holes have so much gravity and they pull things in so tightly, the material that's falling in, if it gets tangled up with the magnetic fields, it can create extremely powerful jets. And so these are jets of material that stretch out from the black hole, or from the sort of accretion disk, not the black hole itself, and they can go for thousands of light years of distance. So black holes are not just this kind of theoretical thing. We see them in the universe. I mean, in terms of the supermassive ones, like, we're here and there's one right there. The center of our galaxy hosts a black hole that's about 4 million times as massive as the sun. And there are a few ways that we know it's there, even though our black hole is not pulling in a lot of matter right now. It doesn't have a big jet coming out. It's not glowing in high energy radiation, just because there's nothing falling in. When a black hole doesn't have anything falling in, it doesn't light up. But every once in a while, it'll get a little sort of dust cloud or a little bit of gas that falls in. And when it does, we can see a little flicker. So this is the central region of the galaxy. And this is zoom in on the very middle part of that there. And this little flickering red thing is a radio source we call Sagittarius A star. And that radio source appears to be due to a little bit of matter every once in a while falling into the black hole. And as it falls in, it sort of goes around and heats up and lets out radiation. In this picture, we're actually seeing it in infrared. But so we can see it through how stuff occasionally falls in, but we can also see the black hole by how stars are orbiting around it. So this is a map of some of the stars around the central black hole. Now we can't see the black hole directly in optical light, but we can mark where we think it is because of watching how these stars are orbiting around some really massive invisible thing. So this is a little movie of several years of the positions of these stars. So you can see them going around, and sometimes they really whip quickly around whatever that thing is. And based on how massive it is and how small it has to be for the stars to get that close to it, it has to be a black hole. There's nothing else that is that compact and that massive. Basically, the way a black hole is defined as a massive thing in a very small space. So we know that there's a black hole in the center of our galaxy. There are other black holes in our galaxy, smaller ones. So when a star runs out of fuel and collapses, if it's a really massive star, sometimes that'll make a black hole. And if it has a neighbor star that's orbiting it, sometimes it will pull the material off of the next door neighbor star. So this is another sort of drawing, but you can have a black hole with a little disk of material, and it can rip the atmosphere off of its companion star. This is called an X-ray binary system, and because the black hole, then the disk around the black hole will heat up and light up in X-ray radiation. And we can make maps of where those are in the sky. So this is a map of the whole sky, projected such that it's in a sort of oval shape, and this is where the disk of the galaxy, the plane of the galaxy is, and that's the center of the galaxy. And these little red These little red dots are where the X-ray binaries are, where the black holes are. So we're really surrounded by these things. There are tons of them in the galaxy. And we can also see very distant supermassive ones when they have these very powerful accretion disks and jets. So this is an illustration of, again, the whole sky. There's the plane of the galaxy. But these circled dots are very distant, very powerful quasars. These are very strong sources of radiation from really distant black holes in the universe. So the thing about looking at these very distant objects is that we're not just looking far away, we're looking back in time. So the reason for that is that light takes time to travel. And so if you look at anything, you're looking at that thing as it was when the light left it and started on its way to you. So it turns out light travels about 1 foot per nanosecond. So if I'm looking at the front row here, I'm looking at about 10 nanoseconds ago. So you're all in the past for me. And then if I look at the back of the room, I'm probably looking at, I don't know, 200 nanoseconds ago. So you're way in the past. And then if I look at the sun with proper eye protection, I'm looking at 8 minutes ago. If I look at the nearest star other than the sun, I'm looking at 4 years ago. And if I look at some of these distant galaxies, I'm looking at billions of years ago. And so you can map out kind of how that corresponds to the age of the universe when that thing was shining, right? So we have the Hubble Space Telescope here. The Hubble Deep Field, that first picture I showed you, was about when the universe was about 1 billion years old. The sources we see in that were from the first billion years of the universe. And then the Ultra Deep Field, we're looking at more like when the universe was 500 million years old. The universe now is about 13.8 billion years old. So we can look at galaxies and quasars that were around in the first billion years of the universe, the universe was very, very young. But it stands to reason that if we look at things that are even farther away, we're going to at some point look at the universe when it was so young that galaxies hadn't even formed yet. So we'll run out of galaxies to look at because if we look too far, there's nothing producing light there to see. But if we look even farther, we can see the universe when it was still just kind of cooling down from the Big Bang. So the Big Bang theory is this idea that the universe in the beginning was in a hot, dense state, and it was glowing with radiation, right? And as the universe expanded and it cooled, and so the radiation and the sort of hot fireball state of the universe sort of cooled down over time. But there was a time when all of the universe was glowing with heat. This was called the hot Big Bang. And it turns out that there are parts of the universe so far away that the heat of the glow from that heat of the hot Big Bang is still coming toward us now. And so we can actually see parts of the universe that, as far as we're concerned, are still in the hot Big Bang. We can see that glow of the early universe. And we see it in every direction, because as you look far enough in any direction, you're looking back in time to 13 point something billion years ago. And so we can see that glow, and we can map it out and sort of see what the sort of temperature of the universe was in every direction. And so when we map it out, it looks kind of like this. So we're again zooming out from the Earth, and there's this kind of sphere in this sort of map of glowing matter, and that's what we call the cosmic microwave background. So this will sort of rotate around a little bit. There are little fluctuations in the temperature, because while the universe was glowing pretty much the same temperature everywhere, there were tiny little places where it was a little bit hotter or a little bit colder. And we can map all that and see in great detail which parts of the universe were a little bit more dense or a little bit less dense. And we can then study sort of how the early universe was laid out, and if there were places that were a little bit more dense, then gravity over time would pull those together and create galaxies and clusters of galaxies, and places that were maybe a little bit less dense might create giant voids in that sort of cosmic web. So we can trace out the connection between those little fluctuations in density of the early, fireball universe to this cosmic web that we see today. So I'm going to talk about a couple of sort of remaining mysteries about the universe. So one of them is my personal favorite, dark matter. This is what I do most of my research about. So dark matter is some kind of matter. So matter is something that has gravity, it has mass, right? So it interacts with gravity. But dark matter is a kind of matter that we can't see, it's invisible. But it turns out that it makes up most of the matter in the universe. So how do we see something that's invisible? Well, it's kind of like if you watch a video like this, you might not be able to easily see that there's a person standing in the middle waving their arms around. But you can see that there's fire moving in really weird ways. And if you look at that, you don't assume, oh, the fire just likes to do that. You figure that there's something making the fire move around like that. There's something twirling it to make that happen. And so that's kind of the way that we see dark matter. We see that things that do emit light are moving in ways that don't make sense based on our understanding of physics. And so there has to be something else going on to make that motion happen. One of the first people to teach us about this was this person, Vera Rubin. She discovered how dark matter acts within galaxies and really convinced the astronomy community that dark matter is a real important thing. So what she was doing is she was looking at spiral galaxies. So again, this is a spiral galaxy much like our own. It has a bulge of stars and gas and dust and a supermassive black hole in the center. And then there are these sort of spiral arms that form a thin disk and stretch out from the center of the galaxy. And spiral galaxies rotate, not like this, but the stars go around the center. And she was studying how the stars move around the center to try to understand how the sort of gravity is distributed through the galaxy. Because if you watch how something rotates, or how something orbits, that tells you about the mass of the thing it's orbiting and how the matter is distributed there. And so what she expected to see was something like this, where you have the bulge in the center, and that's creating most of the gravity. And so if you're closer to the bulge, you're moving really quickly, and if you're farther out, you're moving really slowly. Just like in our solar system, the planets near the center, Mercury and Venus, go really quickly around the sun, and the planets toward the edge go really slowly. That's because the ones toward the middle are feeling that gravity really strongly. The ones toward the outside don't feel it as strongly, and so they move more slowly. If they went too fast, they would escape the galaxy, right? But it turns out what she saw was something quite different. What she saw was something more like this, where in this picture, the stars toward the center and the stars to the edge are actually going the same speed. All of these stars are moving in the same speed. The ones toward the center don't take as long to go around because they're closer in, but they're moving with the same sort of velocity. And that doesn't make sense if all the matter is what you can see, because the stars toward the edge are going so fast, they should just be flying off into space. It's kind of like if you have a merry-go-round and if this kid pushes too fast, this little child will just go flying off into the dirt, right? And if the merry-go-round is going really, really fast and the kid is still holding on, you have to assume that like something's holding him in, like he's got like a little invisible seatbelt or something, because he's just not that strong. And that's what Vera Rubin concluded about these galaxies, that there's something holding those stars in that we just can't see. And we call that dark matter. So the way galaxies really look is there's the stars and the gas and the dust and everything that we can see in the middle, and then much larger than that, extending much farther, is this blob of invisible stuff that provides the extra gravity that holds all these stars in as they're orbiting around the center. And the dark matter not only extends much farther than the galaxy, it's also the vast majority of the matter of the galaxy. So for most galaxies, the dark matter is something like 85% of the matter. The star, all the stuff we can see is kind of an insignificant part of the mass of a galaxy. But that's not the only way that we see the dark matter is there. We also see it in how it affects the shape of space itself. So you might have seen a picture like this before. This is a kind of cartoon illustration of how gravity works in Einstein's idea of relativity. So the idea is that if you have a massive object, it creates this kind of dent in space-time and creates a sort of curvature of space where This is a two-dimensional representation. You have to imagine it like 3D, where the space is kind of pulled in around the object. But things that have mass create these little dents in space. And so if something's trying to move past that thing, the trajectory will be altered by the fact that the space is bent. There's a famous quote about this: matter tells space-time how to curve, space-time tells matter how to move. So if you were an object moving past something that's bent space, then your path would kind of follow that curve. You might orbit around if you're moving really close and really quickly, or you might just be deflected. But it turns out it's not just objects, things that have matter that are affected by the shape of space. Also, light is affected by the shape of space. So light traveling past a massive object, traveling through curved space, will also curve in its path, because it's just like if you have like a fiber optic cable and you put light in one end and you bend the cable around, the light will come out somewhere else. Light moving through curved space follows the curve and bends around. And this is a phenomenon called gravitational lensing. And we can use that to study where matter is in the universe. So this is an illustration of that. If we're here on the Earth and there's a galaxy in the distance, and there's a big cluster of galaxies in the middle, and this cluster of galaxies has a whole lot of dark matter, it has its own massive dark matter halo, the dent in space-time from that massive cluster of galaxies isn't just from the galaxies themselves, but also from this big blob of dark matter. So you end up getting this really big dent. And so the light that's leaving the galaxy doesn't go out in straight lines, and the galaxy doesn't end up being completely hidden by the cluster in between. The light that would sort of pass by the Earth gets bent around to come at the Earth from more than one angle. And it kind of distorts the image of the galaxy, like if you took a giant lens and you held it up in the sky against the background of the galaxy. And we can see that in images of the sky. So this is a picture of a cluster of galaxies, and here you can see these arcs that are the images of distant background objects bent around by that curved space. Here's another example. These are two images of probably the same galaxy in the distance. This is just a sort of ordinary galaxy whose light is sort of stretched and pulled apart grotesquely by moving through this very, very curved space from the cluster of galaxies here, where it doesn't look like that much, but there's a lot of dark matter in that cluster. Again, here's another one where this is just a kind of regular blue galaxy in the background, and its light is bent all around and reproduced over here from the dark matter around this cluster of galaxies. And if you get the alignment just right, you can have a galaxy and something in between, and the light will curve all the way around, and you can get what's called an Einstein ring, where the light is bending all the way around that object. So this is, again, a blue galaxy that in actuality is right behind this thing, but has had its light bent by the matter in between. And every once in a while you can get a little happy face. And these images are not just beautiful and intriguing, they're also really important for studying where matter is laid out in the universe, because the gravitational lensing doesn't care if we can see the matter or not, it just cares how much stuff there is there, and that determines how much the space is bent. And so if we can look at these images and figure out how much space is being bent, that tells us how much the stuff there weighs, how much mass is really there. And that tells us that most of the matter in the universe, by far, is this invisible dark matter. The other cosmic mystery I want to talk about is dark energy. So dark energy and dark matter are not the same thing, and they're probably not related to each other. They're both called dark because we can't see them and we don't know what they are, but they're not two aspects of the same phenomenon or anything else. They actually act pretty differently. The way we found out about dark energy was asking the question, will the universe expand forever? So the universe began expanding at the Big Bang, and it was expanding very quickly. And as the universe expands, the gravity inside the universe kind of pulls back, right? Because the gravity sort of slows down the expansion. And so in the 1990s, astronomers were looking at the expansion of space and trying to figure out, will the universe expand forever? Or will the gravity inside the universe be so strong that it halts the expansion and then everything comes back and ends in a big crunch? it's kind of like asking, if you take a ball and you throw it up into the air, will it go up into the air for a while, stop, and fall down again? Because you just threw a ball up into the air. Or if you're incredibly strong and you throw it at escape velocity, it leaves the Earth's atmosphere and keeps going, but it's always being pulled by the Earth, right? And all you have is that sort of initial push. So they were looking at the universe expanding, and just to clarify, the way the universe expands, the galaxies themselves don't get any bigger, but the space between galaxies gets bigger. So it expands like that. So they were watching the universe expansion. They were trying to determine how quickly it was slowing down. And what they found was actually, instead of slowing down, the expansion was speeding up. And this was really weird. It turns out the expansion was slowing down for the first few billion years, and then something happened and the expansion started speeding up again, which is just like if I take a ball and I throw it up into the air and it's sort of slowing down and then it just shoots off into space. It's pretty much exactly that weird. It's very similar physics. So whatever is making that happen, we call that dark energy. We don't know what it is. The best guess we have at the moment is that it's something called a cosmological constant, which is an idea that traces back to Einstein. It's just a sort of property of space where space has this kind of energy density in it that causes more expansion. And if it is a cosmological constant, then what's going to happen in the future is that the other galaxies will get so far away we won't be able to see them. Our own galaxy, which by that time will have merged with Andromeda galaxy next door, and that'll be really interesting in about 4 billion years. But anyway, our own galaxy, or what's left of our galaxy after that big collision, will be isolated in the universe. Everything else will be so far away we can't see it. Everything else will fade away, and then we'll just be left alone, and the stars in our galaxy will eventually burn out, and we won't have any new stuff coming in to make new stars. And so over time, everything will just kind of fade to black. This is called the heat death of the universe. It's quite a sad story. But we're still trying to understand really what dark energy is, so there's a chance that there's some other way that the universe might end that might be less sad. But this is where things look like they're going in the very distant future of the universe. To review, all right, so we have dark matter, which is the thing that kind of makes these deeper gravitational wells, and we have dark energy that's kind of making the universe expand faster. So they act very opposite. So dark matter, dark energy, dark matter, dark energy. All good? Okay. So if we look at those things together and count up kind of how much of the universe is made of dark matter and dark energy by some kind of accounting of the energy of dark energy and the energy contained in dark matter, and we make a pie chart of this, then we get that the vast majority of the universe is dark energy. Whatever dark energy is, it really dominates the universe in terms of the energy density. Then there's dark matter up there, which makes up the vast majority of the matter in the universe. And then we have this little sort of 5% slice there that represents everything that we can see and touch and interact with. All of the galaxies we see in the sky, everything we remotely understand is in this little 5%. So not only are we not the center of the universe, we're not even an important part by any stretch of the imagination. We're kind of an afterthought on this universe that's dominated by these massively dark, invisible, mysterious forces, right? And that might be kind of a depressing thought that that we're really that insignificant in any sense of the term. But one of the things that reminds me of is this picture from the Voyager 1 spacecraft. So this picture is known as the pale blue dot. It's Voyager looking back toward the sun to see the Earth. So that's the Earth there. So this is from 4 billion miles away, so the Earth looked very small. It was just this little speck of dust. And when I look at this, I think, okay, so we are a speck of dust on a speck of dust on a speck of dust. We are not an important part of the universe in any stretch of the imagination. But the thing about that I find kind of inspiring is that even though we are this completely insignificant speck of dust, We can use our observations and our experiments and our mathematics and our reasoning to understand and observe and comprehend the vast reaches of space and time. You know, we can see the effects of dark matter and dark energy. We can look at the Big Bang and watch it carrying out all around us in the universe. We can see where the galaxies are. We can observe the cosmic web. And we can attack these mysteries like dark matter and dark energy. And as time goes on, you know, our observations will improve, our theories will improve, and hopefully, even as insignificant as we are, we will be able to understand even more. So that's the end of my talk. Thank you for listening.